There is a moment just before you fall asleep when the world stops making noise. The traffic fades, the thoughts slow down, and for just 1 second, you are not anywhere in particular. You are simply here. I want to take you somewhere tonight. Not far, actually. Just up, past the clouds, past the satellites humming quietly above us, past the moon, heavy and silver in the dark, past Mars, past Jupiter, past everything we were taught to name in school, out to where the real story begins. Because tonight, we are going to talk about the Milky Way, our home, not the planet, not the solar system, the whole galaxy, the enormous, spinning, ancient, impossible structure that contains everything you've ever known, everyone you've ever loved, and every single thing that has ever happened in the history of human experience. All of it inside this one galaxy. I want to tell you 100 things about it. Some will surprise you. Some will make you feel very, very small in the best possible way. And some might just change the way you look at the sky forever. So close your eyes if you want. Get comfortable and let's go. The Milky Way is a spiral galaxy, not a ball, not a cloud. A spiral like a pinwheel caught in slow motion, arms curling outward from a bright, dense center, turning through space with a patience that makes human time feel like a blink. I always found that beautiful, that of all the shapes the universe could have made our home a cube, a smear, a formless blob. It chose a spiral, the most elegant shape in nature, the same shape as a nautilus shell, the same shape as a hurricane seen from space, the same shape as water draining from a bathtub. There is something in the universe that loves spirals, and our galaxy is one of them. The Milky Way is about 100,000 light years across. Let that number sit for a moment. A light year is the distance light travels in 1 year, nearly 9.5 trillion kilometers. And the Milky Way stretches 100,000 of those. If you tried to drive across the Milky Way at highway speed, let's say 100 kilometers per hour, it would take you approximately 1 quintillion years to cross it. 1 quintillion years. The universe itself is only 13.8 billion years old. You would need to live through the age of the universe 72 million times over just to make the drive. There is no number large enough in everyday language to make that feel real. And yet, here we are, inside it. Our solar system is not at the center of the Milky Way. For a long time, humans assumed we were special, that our sun must sit at the heart of things, at the glowing center of the galaxy, throne of the cosmos. We were wrong. We live in the suburbs. Specifically, we are tucked into a minor spiral arm called the Orion Arm, about 26,000 light years from the galactic center. Not the center, not the edge. Somewhere in the quiet middle distance, like a small house on a long street, far from both the city noise and the wilderness. I find that oddly comforting. We are not at the center of everything. We are just here in our little corner. Looking out, the Milky Way is not flat. Well, it is mostly flat, like a disk, but it has a warp. The outer edges of the galaxy are tilted, bent slightly, like a vinyl record that has been left in the sun too long. Scientists believe this warp was caused by the gravitational pull of the Milky Way's two largest satellite galaxies, the Large and Small Magellanic Clouds, tugging on the outer disk over billions of years. The galaxy bends, slowly, silently, like everything alive eventually does. The Milky Way has a bar. No, not that kind. A galactic bar. A long, dense structure made of stars that cuts through the center of the galaxy, connecting the inner ends of the spiral arms. This makes the Milky Way a barred spiral galaxy, a specific type with a rectangular heart. From above, it would look something like a cosmic Catherine wheel, long bar in the middle, arms sweeping out from each end. We didn't always know this. Because we are inside the galaxy, we can't step back and look at it the way you'd look at a photograph. We figured out its shape the way you might figure out the shape of a city you live in by walking its streets, measuring distances, charting the stars around us, slowly, carefully, over many lifetimes of looking up. The Milky Way contains between 100 billion and 400 billion stars. We're not entirely sure of the exact number. Think about that. We are so far inside this thing, so small within it, that we cannot count its stars with precision. We estimate, we model, we extrapolate from what we can see. The honest answer is somewhere between 100 billion and 400 billion suns. Every one of them burning, every one of them ancient. Many of them with planets of their own circling in the dark. Most of the Milky Way is invisible to us, not because it's dark, because it's hidden behind clouds of gas and dust, great drifting nebulae that absorb light, scatter it, make whole regions of the galaxy opaque to our telescopes. For centuries, we could only see a fraction of our own galaxy. It wasn't until we started using infrared telescopes, instruments that detect heat rather than light, that we began to peer through those cosmic curtains and see what was hiding behind them. What we found surprised everyone. More stars than expected, more structure, more complexity. The galaxy is deeper than it looked. It usually is. The Milky Way is about 13.6 billion years old. The universe itself is 13.8 billion years old. That means our galaxy formed almost at the very beginning. When the universe was young and hot and still figuring out what it wanted to be, the Milky Way began to take shape, clouds of hydrogen collapsing under gravity, the first stars igniting, the slow rotation beginning. By the time Earth formed 4.5 billion years ago, the galaxy was already more than 9 billion years old. Our planet is young. The galaxy is ancient beyond words. We are guests in a very old house. The Milky Way is moving. Everything is, of course. But not just orbiting within the local group of galaxies. The Milky Way itself is being pulled across space toward a massive gravitational anomaly called the Great Attractor. We don't fully understand the Great Attractor yet. It is a region of space with such enormous gravitational pull that it is drawing hundreds of thousands of galaxies, including ours, toward it at hundreds of kilometers per second. We are falling towards something we cannot fully see, and we have been for billions of years. There is something in that image I keep coming back to. Something about how much of our journey is invisible to us. From Earth, the Milky Way looks like a faint band of light across the sky. That band, that soft, cloudy streak that ancient people saw and called a river, a road, a river of milk, is actually us looking sideways through the disk of our own galaxy. When you look at that band, you are looking along the plane of the Milky Way, seeing the accumulated light of billions of stars compressed into a single brushstroke. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. And from that, we get our word galaxy, milk. The universe named itself after something as simple and as human as the white liquid a mother gives her child. Light pollution has made the Milky Way invisible to most people on Earth. More than 1/3 of humanity, including 80% of North Americans and 60% of Europeans, cannot see the Milky Way from where they live. The artificial lights of our cities have drowned it out. For the first time in human history, billions of people are growing up without ever seeing their own galaxy in the sky. I think about what that means sometimes. For all of human history, every civilization, every poet, every shepherd lying in the dark looking up the Milky Way was there, constant, overwhelming, a reminder every night that we were small and that the universe was vast, and we covered it with streetlights. The Milky Way rotates, but not like a solid wheel. If you spin a wheel, every point on it completes one rotation in the same amount of time. The outside moves faster than the inside to keep up. The galaxy doesn't work that way. Stars at different distances from the center orbit at different speeds, and in a way that should, by the laws of physics, cause the spiral arms to wind up and disappear over time. They don't. This is one of the great puzzles of galactic dynamics. The spiral arms persist. They maintain their shape over billions of years. How? The current best explanation is that the arms are not made of the same stars all the time. They're more like a traffic jam, a wave of density moving through the galaxy, and stars bunch up as they pass through it, creating the illusion of fixed arms. The arms are not made of stars. They are made of crowding. I had to sit with that for a while when I first read it. The Milky Way has satellite galaxies, small, irregular collections of stars that orbit our galaxy the way moons orbit planets. The most famous are the Large and Small Magellanic Clouds, visible as fuzzy patches of light from the southern hemisphere, close enough that ancient navigators used them to find their way across the Pacific Ocean. But there are many others: dwarf galaxies, globular clusters loosely bound to us, stellar streams, the ghostly remnants of smaller galaxies our Milky Way has already consumed, stretched out into long arcs of stars that circle the galaxy like smoke rings. The Milky Way has eaten other galaxies, and their bones are still visible if you know where to look. At the very center of the Milky Way is a supermassive black hole. It is called Sagittarius A*. It has a mass 4 million times that of our Sun, 4 million suns, compressed into a single point. And it sits at the exact center of our galaxy, the dark heart around which everything, every star, every planet, every cloud of gas, every nebula, every world that has ever harbored life slowly, inexorably orbits. We orbit a black hole. All of us, right now, Sagittarius A times is relatively quiet. For a supermassive black hole at the center of a galaxy, it consumes surprisingly little material. Some galactic centers are intensely active, great jets of energy extending millions of light years into space, entire regions of the galaxy illuminated by the immense force of matter falling into the depths. Ours is calm, almost serene. Astronomers call these active galactic nuclei quasars, and they are among the most powerful events in the universe. The Milky Way had a quasar phase billions of years ago, when the black hole was younger and drawing in far more material. Now it rests. The immense gravitational force at the center of our galaxy has grown still. And so, I suppose, should we? Part 2, Stars Without End. Fact 1632, the stars of the Milky Way. The Sun is an average star. I know we were taught it was special, and in the context of our lives, it is everything. It is the reason liquid water exists on Earth, the reason photosynthesis works, the reason any of this is possible. But in the context of the Milky Way, the Sun is deeply ordinary. Medium size, medium temperature, medium age, medium brightness, a yellow dwarf star, astronomers call it, one of hundreds of billions just like it. And somehow, out of all those billions, this one ordinary star in this ordinary corner of the galaxy happened to have a rocky planet at just the right distance with just the right chemistry for life to begin. Ordinary circumstances, extraordinary result. The largest stars in the Milky Way are incomprehensibly immense. The star Uy-Scuti, located about 9,500 light-years from Earth, has a radius approximately 1,700 times that of our Sun. If you placed Uy-Scuti where the Sun is, its surface would extend past the orbit of Jupiter. Jupiter, the planet we consider our solar system's giant, the planet that could hold 1,300 Earths inside it, would be fully contained within the star. And Uy-Scuti is not even the largest star we know of. There may be stars out there still undiscovered that make even these giants look small. The Milky Way is full of things that go far beyond the scale of our imagination. Most stars in the Milky Way are red dwarfs, not the immense supergiants, not our yellow sun. The majority, perhaps 70 to 75%, are small, dim, cool red dwarfs. They burn so slowly and so efficiently that some of them will live for trillions of years. The universe is only 13.8 billion years old. These stars will still be burning when the universe is 100 times older than it is now. When our sun is long gone, when the earth has faded into memory, when everything we recognize as the night sky has changed beyond recognition, red dwarfs will still be burning. Patient, quiet, almost eternal. Stars are born in clouds of gas and dust called nebulae. The word nebula is Latin for cloud. These are the nurseries of the galaxy, vast regions of hydrogen and helium, sometimes hundreds of light years across, slowly condensing under the pull of gravity. Clumps form. The clumps grow denser. The pressure at the center rises. The temperature climbs. And then ignition. A new star switches on. It has happened in this galaxy hundreds of billions of times. It is happening right now, somewhere in the deep space between the spiral arms. A star being born tonight. The Orion Nebula is the closest stellar nursery to Earth. About 1,344 light years away, it is visible to the naked eye as the middle point in Orion's sword, a soft, slightly diffuse light that ancient people probably thought was a star but could never quite bring into focus. It is not a star. It is a cloud 24 light years across, glowing with the light of thousands of young stars freshly born within it. When you look at Orion's sword on a clear night, you're looking at a place where creation is happening right now. New worlds being made, new suns lighting up for the first time, all visible with the naked eye from your backyard. Stars reach the end of their lives. They do not burn forever. The way a star concludes its journey depends on its size. Small stars like red dwarfs will slowly cool over trillions of years, fading into cold, dim objects called black dwarfs. Medium stars like our sun will expand into red giants, gradually drawing in their inner planets, then release their outer layers in a beautiful expanding shell called the planetary nebula, leaving behind a warm, dense core called a white dwarf. Larger stars conclude their lives with something far more striking. They release a final, extraordinary burst of energy outward into space. A supernova is one of the most energetic events in the universe. When a massive star runs out of fuel, its core collapses in a fraction of a second, and the resulting explosion releases more energy than our sun will emit in its entire 10 billion year lifetime. For a few weeks, a single supernova can outshine an entire galaxy, billions of stars. One explosion, brighter than all of them combined. The Milky Way produces roughly one supernova every 50 to 100 years. The last one visible to the naked eye from Earth was in 1604, seen by Johannes Kepler, who watched it blaze in the sky for over a year. we are overdue for another. Every heavy element in your body was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now. These elements did not exist at the beginning of the universe. The Big Bang produced only hydrogen, helium, and tiny amounts of lithium. Everything else, every atom heavier than those, was created inside a star through the process of nuclear fusion and scattered into space when that star died. You are made of stardust, not as a metaphor, literally, physically, chemically. The atoms in your body were processed inside stars that died before a sun was born. You are the Milky Way looking at itself. After a supernova, what is left behind depends on how massive the star was. Medium massive stars leave a neutron star, an object so dense that a teaspoon of its material would weigh about 1 billion tons. The most massive stars leave something even stranger. They leave a black hole, a point where gravity is so strong that not even light can escape. The Milky Way contains millions of stellar mass black holes, the remnants of massive stars that have already lived and died. Millions of invisible points scattered through the galaxy, bending space around them, swallowing light. We will never see most of them, but they are there. Some stars in the Milky Way are older than the galaxy itself. This sounds impossible, but it is true. Some of the oldest stars in the Milky Way, found in ancient globular clusters orbiting the galaxy's halo, are estimated to be 13.2 to 13.4 billion years old. The Milky Way is 13.6 billion years old. These stars formed so early in the universe's first few 100 million years that they predate the galaxy as we know it. They were among the building blocks from which the Milky Way was assembled. Stars older than the galaxy, witnesses to the very beginning. Stars move. Not just orbiting the galaxy, they drift individually through space. The sun is currently moving through the galaxy at about 828,000 kilometers per hour. That is not its speed relative to nearby stars, it is its speed relative to the center of the galaxy as it orbits. 828,000 kilometers per hour. And yet, because all the stars around us are moving at similar speeds in similar directions from our perspective, it feels like stillness. Like driving on a highway where every car is going the same speed. Relative to each other, everything seems almost stationary. But relative to the universe, we are flying. The Milky Way has stellar streams, rivers of stars. When a small galaxy or globular cluster passes too close to the Milky Way, our gravity tears it apart, stretching it into a long ribbon of stars that traces the orbit of the destroyed object. These stellar streams are ghostly remnants, the scattered bones of things our galaxy consumed long ago. The Sagittarius stream is the most prominent, a river of stars that wraps almost completely around the Milky Way, the remains of the Sagittarius dwarf galaxy, which our galaxy is currently in the process of absorbing. We are eating a galaxy right now, slowly, without drama, the way a tide wears down a cliff. Some stars in the Milky Way are hypervelocity stars, moving so fast, up to 700 kilometers per second, that they are escaping the galaxy entirely. Flung outward, it is believed, by gravitational interactions near the central black hole or by the explosion of a companion star in a binary system, these stars are leaving. Permanently, they will drift out past the edge of the galaxy into the vast, empty intergalactic space and continue moving forever alone in the dark between galaxies. I think about those stars sometimes, exiled, moving away from everything, and somehow still burning. The night sky, as we see it, is a lie, not an intentional one, just a consequence of physics. When you look at a star, you are not seeing it as it is now. You are seeing it as it was when the light you're watching left it sometimes hundreds, thousands, or millions of years ago. The stars in the night sky exist at different depths in time. Some of what you see no longer exists. Stars that have already died, already exploded, already collapsed, their light is still traveling toward us and will continue to arrive for centuries after their death. The night sky is a museum. Every photon is an artifact. The Milky Way is a cannibal. Over its 13.6 billion year history, it has consumed dozens of smaller galaxies, drawn them in with gravity, shredded them apart, absorbed their stars into its own structure. This is not unusual. It is how galaxies grow. The Milky Way we live in today is partly made of material from other galaxies, stars born in entirely different systems, in entirely different corners of the early universe, now orbiting alongside stars that were born here. Immigrants and natives, all mixed together, all circling the same black hole now. There is a globular cluster orbiting the Milky Way called Omega Centauri. It contains approximately 10 million stars, packed into a sphere only 150 light years across. It is the largest and most massive globular cluster associated with the Milky Way. So large, in fact, that some astronomers believe it is not truly a globular cluster at all, but the stripped core of a small galaxy our Milky Way consumed long ago, the heart of something that used to be a galaxy, still intact, still orbiting, still holding its stars together after everything else was taken from it. The oldest known star in the Milky Way is called Methuselah star HD 140283. It is estimated to be approximately 13.7 billion years old. For reference, the universe is 13.8 billion years old. This star formed when the universe was barely 100 million years old. It has been burning quietly ever since. It has watched the Milky Way form around it, watched our sun switch on, watched Earth cool from a molten ball to a living world. It is still there, 190 light years from Earth, visible through a small telescope, the oldest thing you will ever see. The Milky Way contains hundreds of billions of planets. We used to think planets were rare. Until 1992, we had never confirmed a planet outside our solar system. The idea that other stars had worlds orbiting them was theoretical, plausible, but unproven. Then we found one, and then more, and then the floodgates opened. As of today, we have confirmed over 5,000 exoplanets worlds orbiting other stars, and the data suggests that virtually every star in the galaxy has at least one planet. Hundreds of billions of planets in one galaxy. Among hundreds of billions of galaxies, the universe is full of worlds. Many of those planets are in the habitable zone of their star. The habitable zone, sometimes called the Goldilocks zone, is the range of distances from a star where liquid water could exist on a planet's surface. Not too hot, not too cold, just right. We currently estimate there are tens of billions of rocky planets in the habitable zones of stars in the Milky Way alone. Tens of billions of worlds where the temperature is right for oceans, where life, as we understand it, could exist. The first exoplanet ever confirmed orbited a pulsar, not a quiet, sun-like star. A pulsar, the rapidly rotating remnant of a supernova, blasting beams of radiation into space with clockwork precision. It was 1992. The planet was found by astronomers Alexander Wolszczan and Dale Frail. And the world was strange, a world that survived the death of its star. a world being bathed in radiation, a world nothing like Earth, but a world. The universe's first confirmed answer to our question. Yes, there are other planets. The most common type of planet in the Milky Way may be super Earths. Planets larger than Earth but smaller than Neptune, too big to be rocky like us, too small to be gas giants. We don't have one in our solar system, but they appear to be everywhere else, which means our solar system may be the unusual one, the rare one, the one that doesn't fit the pattern. There is a planet in the Milky Way that it rains glass. HD 189733b is a gas giant about 64 light years from Earth. It has winds of over 8,000 kilometers per hour. Its atmosphere contains silicate particles, tiny shards of glass that are whipped around the planet at those speeds. It rains glass sideways at 8,000 kilometers per hour. And its surface temperature is around 1,000 degrees Celsius. The universe makes things that have no analog in our experience, things that require entirely new words. There is a planet where it snows sunscreen. Kepler 1.3ab is a gas giant so close to its star that its atmosphere reaches temperatures where titanium oxide, a compound found in sunscreen, condenses out of the air. On the night side of the planet, where temperatures drop slightly, titanium oxide snow falls from the sky. Snow made of sunscreen. On a planet almost 3 times the size of Jupiter, in a galaxy full of impossibilities. Some exoplanets orbit 2 suns, circumbinary planets, worlds with double sunsets, twin shadows, complex seasons determined by the changing geometry of 2 stars moving around each other. The first confirmed circumbinary planet, Kepler 1.6b, was nicknamed Tatooine, after the fictional desert planet from Star Wars. Science fiction became science fact. And somewhere out there, on a world like that, something might be watching 2 suns set over an alien horizon. The Milky Way may contain rogue planets, planets with no star, worlds that formed around the star and were then ejected by gravitational chaos during the early solar system, flung out into interstellar space, wandering the dark between stars forever. No sun, no light, no warmth from above, just cold, perpetual night. And yet some scientists speculate that if such a planet had a thick enough hydrogen atmosphere or internal heat from radioactive decay, it might maintain liquid water beneath its surface. Life, perhaps, in the dark, on a planet with no sun, drifting through the galaxy alone. The Milky Way is ancient enough to have hosted life long before Earth existed. If life arose on some of those billions of habitable zone planets, even just a few, it could have had billions of years head start on us. Civilizations that rose and fell before the first fish crawled out of Earth's oceans. Technologies we cannot imagine. Histories that no one living today will ever know. The galaxy may have been full of stories we will never read. We have not found any other life in the Milky Way. Not yet. The silence is called the Fermi paradox, named for physicist Enrico Fermi, who in 1950 looked at the mathematics of the galaxy and asked a simple question: given how many stars there are, how many planets there are, and how much time there has been, where is everybody? We should, by the numbers, have found signs of life by now. We haven't. Why? Nobody knows. Maybe life is rarer than we think. Maybe it arises often but doesn't last. Maybe they are out there and we simply haven't looked in the right direction yet. Or maybe, and this is the thought I find most unsettling, the silence is telling us something important, something we haven't understood yet. The search for life in the Milky Way is one of the most important projects in human history. SETI, the search for extraterrestrial intelligence, has been scanning the skies for radio signals for over 60 years. We have found some interesting anomalies, the most famous, the WOW signal. In 1977, astronomer Jerry Amon was reviewing data from a radio telescope when he saw a signal so strong, so structured, so unlike background noise that he circled it on the printout and wrote "wow" in the margin. It came from the direction of Sagittarius. It lasted 72 seconds. It was never detected again. To this day, no one knows what it was. Our own solar system is unusual in how orderly it is. Many exoplanetary systems we've discovered are chaotic giant planets in close, blistering orbits around the stars, rocky planets flung to strange distances, orbital resonances that defy our models. Our system, with its giant planets in the outer reaches acting as gravitational shields, protecting the inner rocky planets from a constant bombardment of comets and asteroids, may be rare. Jupiter, in particular, has likely deflected countless objects that would otherwise have hit Earth. Jupiter is, in some sense, our guardian, the giant watching over the inner system, the reason we are still here. Saturn's rings are a relatively recent feature of our solar system. For billions of years, Saturn may have had no rings or much smaller ones. The current ring system is estimated to be between 10 and 100 million years old. That means when dinosaurs walked the Earth, Saturn's rings may have just been forming. The solar system is still changing, still evolving, still surprising us. Europa, one of Jupiter's moons, has a liquid ocean beneath its icy surface, an ocean larger than all of Earth's oceans combined, kept liquid not by sunlight, but by the gravitational flexing of Jupiter's massive pull tidal heating, the same process that drives volcanic activity on Io. No sunlight, no surface, a world ocean locked under kilometers of ice. And in that ocean, heated by hydrothermal vents on the seafloor, there may be life. Simple life, microbial life, but life in our own solar system, hiding under the ice of a moon of Jupiter. Enceladus, a moon of Saturn, is actively venting water into space. Geysers of water vapor and ice erupting from cracks near its south pole, shooting material hundreds of kilometers above the surface. We have flown through those plumes. The Cassini spacecraft detected organic molecules in them, complex carbon compounds, the building blocks of life coming from inside the moon. Something is happening under the ice of Enceladus. We don't know what. We need to go back. Titan, Saturn's largest moon, has lakes and rivers and rain, not of water, of liquid methane. The temperatures on Titan are around negative 180 degrees Celsius. Water is rock hard there. But methane, a gas at Earth, temperatures flows as a liquid. There are methane seas, methane beaches, methane rain falling from orange methane clouds. An entire hydrological cycle, not of water, but of hydrocarbon. Could life exist there? Life based on methane chemistry rather than water? We genuinely don't know. The question is open, and the answer, whatever it is, will change everything. Mars once had rivers. We have photographed the dried riverbeds, the ancient floodplains, the delta where a river once met a lake billions of years ago when Mars was warm and wet and covered in liquid water. It lasted perhaps 1 billion years, that warm, wet period, long enough for life to arise? We don't know. We are looking. Right now, a rover the size of a car is driving across the surface of Mars, drilling into ancient rocks, collecting samples, searching for any trace of what might have lived there once. The search is happening. As you listen to this, tonight, There may be a ninth planet in our solar system, not Pluto. Pluto was reclassified, and that is a whole other story. But beyond Neptune, in the outer darkness of the solar system, the orbits of certain distant objects behave in a way that suggests they are being gravitationally influenced by something large and unseen, something with perhaps 10 times the mass of Earth, moving in a vast, slow orbit, hundreds of times farther from the Sun than we are. Planet 9. We haven't found it yet, but the math suggests it is there, hiding in the dark, waiting to be found. Most of the Milky Way is made of something we cannot see, touch, or directly detect. Dark matter. It does not emit light. It does not absorb light. It does not interact with normal matter in any way we can currently measure except through gravity. And yet we know it is there, because without it, the Milky Way should not exist. The stars in the outer regions of the galaxy orbit too fast. By the laws of physics, by Newton, by Einstein, they should be moving slower. The gravity from the visible stars and gas alone is not enough to hold them in their orbits at those speeds. Something else is holding them, something we cannot see. Dark matter. It makes up approximately 85% of all matter in the universe. We are made of the rare stuff, the unusual stuff. Everything we have ever seen, touched, built, loved, all of it, is only 15% of the matter in the cosmos. Dark matter forms a halo around the Milky Way, an enormous, roughly spherical cloud of invisible material extending far beyond the visible disk of the galaxy. The dark matter halo is thought to be several 100,000 light years in diameter, much larger than the visible galaxy itself. We live inside a vast, invisible structure. The galaxy we can see is just the luminous core of something far, far larger. We do not know what dark matter is made of. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that would have the right properties. But despite decades of searching underground detectors, particle colliders, space telescopes, we have never directly detected a single WIMP. Other theories suggest dark matter could be primordial black holes formed in the very early universe before any stars existed. Or it could be something else entirely, something we haven't thought of yet. The honest answer in 2025 is we don't know. One of the most abundant things in the universe, and we cannot identify it. Dark energy is even stranger than dark matter. It is not matter at all. It is a property of space itself, an energy that permeates the vacuum of the universe and is causing space to expand at an accelerating rate. It makes up approximately 68% of everything in the universe. Dark matter is 27%. Normal matter, stars, planets, gas, dust, everything we can see is just under 5%. 5%. We are 5% of what exists. The rest is invisible, unknown, strange, beyond our current understanding. Because of dark energy, the universe is expanding, and the expansion is speeding up. Distant galaxies are moving away from us, and the farther they are, the faster they recede. There is a point, a cosmic horizon, beyond which galaxies are already moving away from us faster than the speed of light. Not because they are traveling faster than light, but because space itself is expanding faster than light can cross it. Those galaxies are already beyond our reach, already gone. We will never be able to see them, reach them, or communicate with them. The observable universe is shrinking, slowly, imperceptibly, but it is shrinking. In the far future, the Milky Way will be alone. All other galaxies, as dark energy continues to accelerate the expansion of the universe, will eventually move beyond the cosmic horizon. They will become invisible, unreachable, If some civilization exists in the Milky Way a trillion years from now, they will look out at the sky and see nothing. No other galaxies, no other lights in the darkness beyond our local group. Just the Milky Way and its nearest neighbors, alone in an expanding void. They might conclude, looking at that empty sky, that the universe contains only one galaxy. They would be wrong, but they would have no way of knowing. We are fortunate to live when we do, to see the universe before it gets too lonely. The Milky Way and the Andromeda Galaxy are on a collision course. In approximately 4.5 billion years, Andromeda, the nearest large galaxy to the Milky Way, currently about 2.5 million light years away, will collide with our galaxy. The two galaxies will pass through each other, their stars gravitationally perturbing each other's orbits, their gas clouds colliding and triggering massive waves of star formation. It will take about 1 billion years for the collision to complete, and at the end of it, the two galaxies will have merged into a single, larger elliptical galaxy. Astronomers already have a name for it, Milky Way. Despite the collision, virtually no stars will actually hit each other. Galaxies are mostly empty space. The distance between stars is so vast that even when two galaxies collide and interpenetrate, the probability of any two stars actually colliding is almost zero. It will be a collision of gravity and gas and chaos, but the individual stars will pass right through each other like two swarms of bees flying through each other. The shapes will distort, orbits will change, star formation will surge. But the stars themselves, nearly all of them, will survive. Our sun will likely survive the Andromeda collision, but its orbit will be profoundly altered. The sun, which currently orbits the galactic center every 225 to 250 million years, will find itself in a completely different region of the newly merged galaxy. Earth, if it still exists, will orbit a star in a galaxy, nothing like the one we live in now. A reminder that nothing on the longest timescales is permanent, not even the shape of home. The structure of the universe looks like a web, the cosmic web. Galaxies are not randomly distributed. They clump into clusters, clusters join into superclusters, and superclusters are connected by long filaments of matter, like threads in an enormous three-dimensional web. Between the filaments are vast voids, regions of space hundreds of millions of light years across, where almost no galaxies exist. The Milky Way is part of a supercluster called Laniakea, a name taken from Hawaiian meaning immeasurable heaven. Laniakea contains 100,000 galaxies and spans 520 million light years. And Laniakea itself is just one node in the cosmic web. The universe is bigger than any number can hold. The Milky Way is part of the local group, a collection of about 54 galaxies gravitationally bound to each other, including the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. In the vastness of the cosmic web, the local group is our neighborhood, a small cluster held together by gravity, drifting through the universe together. Everything outside it is, in the deepest sense, very far away. The Milky Way is moving toward the Andromeda Galaxy at about 110 kilometers per second. Every second, we are 110 kilometers closer to our future collision. As you listen to this, as you breathe slowly and let sleep approach 110 kilometers. Between galaxies, space is not empty. The intergalactic medium, the diffuse material between galaxies, consists of hot ionized gas, tendrils of dark matter, and occasional rogue stars flung from their galaxies. It is not a vacuum in the purest sense, but it is about as close to nothing as anything in the physical universe gets. 1 atom per cubic meter. On average, the observable universe contains roughly 2 trillion galaxies. 2 trillion, each containing hundreds of billions of stars, each star potentially with planets, each planet potentially with life. The mathematics of the universe are so enormous that even if life arose on one in a trillion planets, there would still be thousands of other living worlds. The universe is either full of life, or it created it once and then stopped. Both possibilities are staggering. We will never travel to another galaxy in the age of our civilization. Not because we lack the technology, though we certainly do, but because the distances involved are so vast that even at the speed of light, crossing from the Milky Way to Andromeda would take 2.5 million years. A civilization that departed today would arrive in a galaxy whose composition it could not predict, around a star it could not know in advance. The Milky Way is our home, not just culturally. It is our home physically. We are bound here by physics, by the hardest limits the universe imposes. In 1995, the Hubble Space Telescope was pointed at a tiny, dark patch of sky, a region roughly the size of a grain of sand held at arm's length, a region that appeared to contain nothing, and the telescope stared at it for 10 consecutive days. What came back was the Hubble Deep Field, an image showing nearly 3,000 galaxies in a region of sky previously thought to be empty. 3000 galaxies, each containing hundreds of billions of stars. In an area of sky the size of a sand grain, the image changed how we understood the universe. It was the universe saying, "You have no idea how much is here." The Hubble Space Telescope has been operating for over 30 years. Launched in 1990, serviced 5 times by astronauts, it has produced more than 1.5 million observations. It has measured the age of the universe. It has confirmed the existence of dark energy. It has photographed galaxies billions of light years away. It has watched stars die and be born. It has changed astronomy more than any instrument since Galileo's first telescope. And it is still operating today. A 30-year-old machine out there in the dark above us, still looking. The James Webb Space Telescope launched on Christmas Day, 2021, and the images it returned were unlike anything anyone had seen. Galaxies from 13.1 billion years ago, galaxies formed only 600 million years after the Big Bang, photographed in stunning detail. The first light of the universe, we are seeing for the first time what the Milky Way looked like before it was the Milky Way. We are watching our own origin. The Milky Way has a smell. Not that you could ever experience it. The fragrance of deep space is distributed over parsecs of vacuum. But the dust clouds near the center of the galaxy, particularly near the molecular cloud Sagittarius B2, contain ethyl format, a compound that smells like raspberries and rum. The galactic center smells like raspberries and rum, chemically. If you could somehow compress the entire experience of standing in those dust clouds into something your nose could detect, that is what it would smell like. Raspberries and rum. Sound cannot travel through space. There is no medium for it. The famous tagline, "In space, no one can hear you scream," is physically accurate. But in dense regions of gas nebulae, the atmospheres of planets' sound can propagate. NASA's Chandra X-ray Observatory detected sound waves propagating through the hot gas surrounding a distant galaxy cluster, the Perseus cluster. Waves with a frequency so low, a B flat, roughly, that it is 57 octaves below middle C, a note that has been playing for billions of years. A note too low for any human ear to ever hear. The universe has a voice, We just can't hear it. The Milky Way rotates once every 225 to 250 million years. This is called a galactic year or a cosmic year. In the history of Earth, our planet has completed about 18 to 20 galactic orbits. When the dinosaurs appeared about 230 million years ago, we were at roughly the same point in our galactic orbit that we are now. We have come exactly once around the galaxy since the first dinosaurs walked the Earth. One galactic year, one rotation, and in that time a species evolved from apes, built cities, sent robots to Mars, and learned to decode the light of stars. The light arriving at your eyes from the night sky is a mixture of many different times. The moon, 1.3 seconds ago. The sun, 8 minutes ago. The nearest star, Proxima Centauri, 4.2 years ago. The Andromeda Galaxy, visible to the naked eye on a dark night, 2.5 million years ago. When you look at the Andromeda Galaxy, you're seeing light that left it when Homo habilis, one of our earliest human ancestors, was just beginning to chip flint into tools on the African savanna. The sky is not the present tense. It is the past, layer upon layer upon layer. There is a great wall of galaxies. The Sloan Great Wall, a massive structure of galaxy clusters and superclusters, stretches across approximately 1.37 billion light years of space. For a long time, it was the largest known structure in the universe. Then we found the Hercules Corona Borealis Great Wall, 10 billion light years across. To put that in context, the observable universe is 93 billion light years in diameter. This structure spans more than a tenth of it. The universe makes things we have no words for. The Milky Way is inside a void, called the local void, a region of unusually low galaxy density that our galaxy sits on the edge of. The local void is approximately 150 million light years across, and it is pushing the Milky Way outward. The slightly lower gravity on the void side relative to the dense regions on the other side creates a net force, gently shoving us toward the great attractor. We are being pushed from behind and pulled from the front, and we don't feel a thing. Every second, the universe produces new stars. Across all the galaxies in the observable universe, approximately 275 million new stars ignite every day, about 3 per second. As you listen to this sentence, 3 new suns lit up somewhere in the cosmos. Every second, the universe produces new stars. Across all the galaxies in the observable universe, approximately 275 million new stars ignite every day, about 3 per second. As you listen to this sentence, 3 new suns lit up somewhere in the cosmos. Stars come in many colors. The color of a star tells you its temperature. Blue stars are the hottest, burning at 30,000 degrees Celsius or more. Yellow stars, like our sun, burn at around 5,500 degrees Celsius. Red stars are cooler, around 3,500 degrees. The night sky, to a sensitive instrument, is not black and white. It is a painting in blue and white and yellow and orange and red, a color-coded map of temperature and age and mass. The sky has always been in color. We just needed the right instruments to see it. Neutron stars has been incredibly fast. The fastest known pulsar, PSR J17482446, rotates 716 times per second, 706 rotations per second. The equator of that star is moving at about a quarter of the speed of light. An object the size of a city rotating 716 times per second. If it was spinning much faster, it would tear itself apart. It is right at the edge of what physics allows. There are stars that pulsate, variable stars, they brighten and dim in regular cycles, like a slow heartbeat, the most famous Cepheid variables. Cepheids pulsate in cycles directly related to their true luminosity. A star that pulsates slowly is intrinsically brighter than one that pulsates quickly. By comparing a Cepheid's apparent brightness to its true brightness, astronomers can calculate its exact distance. Cepheids are the measuring sticks of the cosmos, the first reliable way we had to measure distances beyond our galaxy. Stars with heartbeats that we use as rulers. Two neutron stars merging produces gold. The collision of two neutron stars, an event called a kilonova, generates conditions so extreme that it produces heavy elements: gold, platinum, uranium. All the gold on Earth, every ring, every coin, every circuit board was created in a neutron star merger before our solar system formed, then scattered into the cloud of gas and dust from which the Earth eventually condensed. Gold is older than the Earth, older than the Sun. It was forged in violence in the collision of impossibly dense objects billions of years before any of us existed. And we shape it into jewelry and call it precious. We have no idea how precious it really is. The Milky Way has structure we are still discovering. In 2020, astronomers announced the discovery of a break in one of the galaxy's spiral arms, a spur of stars angled differently from the main arm, suggesting the arm is not as smooth and simple as we thought. The Milky Way is more complex than our models, more detailed, more surprising. After thousands of years of studying it, we are still finding new things. The galaxy is not finished being understood. It may never be. The Sun has about 5 billion years left. In 5 billion years, the Sun will exhaust its hydrogen fuel and begin to expand into a red giant swelling outward until it engulfs Mercury, Venus, and possibly Earth. The oceans will boil. The atmosphere will be stripped away. Everything that has ever lived on Earth, every civilization, every memory, every story will be gone. But 5 billion years is an incomprehensible amount of time, more time than has passed since the Earth formed, more time than there has been complex multicellular life. It is not something to fear. It is simply the natural lifespan of a star. And when the Sun dies, its ashes, the white dwarf left behind, will continue to exist for trillions of years. The Sun will outlast its own death. In 100 trillion years, the last stars will go out. Not the death of a single star, the death of all stars. As the universe ages, star formation slows, the supply of hydrogen available to form new stars dwindles, existing stars burn out, white dwarfs cool. In 100 trillion years, the last red dwarf in the Milky Way, still burning with miserly efficiency, will exhaust its fuel and go dark. The galaxy will fall silent. No more starlight, just the cold remnants, white dwarfs, neutron stars, black holes, drifting in the dark. This era has a name in physics. It is called the degenerate era. And after it comes the black hole era. And after that, the dark era. The universe has a very long, very quiet future ahead of it. Black holes will eventually evaporate. In 1974, Stephen Hawking showed mathematically that black holes are not truly permanent. They slowly emit radiation, losing mass in the process. This is called Hawking radiation. For a stellar mass black hole, the process takes an almost incomprehensible amount of time, approximately 10 to the power of 67 years. For Sagittarius A times the supermassive black hole at the center of our galaxy, the evaporation time is approximately 10 to the power of 87 years. Numbers so large they have no meaning in everyday language, but finite. Eventually, even the black hole at the center of the Milky Way will evaporate, a faint burst of radiation, and then nothing. The story over. But before all that, long before the Andromeda collision will happen, and it will be spectacular. When Andromeda and the Milky Way first approach each other, the night sky from Earth, if anything is still alive on Earth, will show Andromeda growing larger and larger, not a small fuzzy patch. A full galaxy spread across the sky, its spiral arms stretching from horizon to horizon, the most dramatic sight the human eye has ever seen. A galaxy filling the sky. After the merger, the new galaxy Milkomeda will settle into an elliptical shape. No more spiral arms, no more elegant pinwheel, just a large, rounded elliptical galaxy full of old stars with very little new star formation. The wild, creative spiral phase will be over. The galaxy will have grown up, quieter, more settled, old. The merger will likely trigger a burst of star formation. When the gas clouds of two galaxies collide, they compress, heat up, and collapse into stars by the billions. For a few 100 million years, the merged galaxy will blaze with newborn stars. A final flourish, a last great creative act. Before the slow fate begins, the Earth will not survive to see the Andromeda collision. In about 1 billion years long before Andromeda arrives, the sun will have brightened enough that Earth's oceans will evaporate. The greenhouse effect will run away. The surface will become uninhabitable. If humanity still exists, if it has not left, not evolved into something unrecognizable, not died out, it will need to have found another home long before then. The Earth is temporary. All worlds are. We have already sent messages to the stars. The Voyager 1 and Voyager 2 spacecraft launched in 1977 have crossed the boundary of the solar system and are now in interstellar space. They carry golden records, engraved with sounds and images from Earth, music, voices, greetings in 55 languages, the brainwaves of a woman in love, the sound of rain, the cries of whales. They are moving at approximately 60,000 kilometers per hour. At that speed, it will take Voyager 1 about 40,000 years to come close to another star. But they are out there, human message, drifting through the Milky Way, carrying the sound of rain. Voyager 1 is the most distant human-made object in existence. As of 2025, it is approximately 24 billion kilometers from Earth. The signal from its transmitter traveling at the speed of light takes over 22 hours to reach us. And the transmitter is powered by a small nuclear generator producing about 4 watts of electricity. 4 watts, less than a nightlight, and it is communicating from 24 billion kilometers away. Engineering is a kind of miracle sometimes. The Pioneer plaques are another message to the stars. Affixed to Pioneer 10 and 11, launched in 1972 and 1973, they are gold anodized aluminum plates engraved with a drawing of a man and woman, our location in the galaxy relative to 14 pulsars, and a diagram of our solar system, an attempt to introduce ourselves in case anyone finds the spacecraft, in case anyone anywhere in this 100,000 light-year-wide galaxy ever encounters a small metal object tumbling through space and wonders where it came from. We left our name and address, just in case. The Milky Way itself might be hosting life right now, not just on Earth, possibly on a moon of Europa or Enceladus, possibly on worlds around other stars. Life forms completely unlike us, different chemistry, different biology, different experience of the universe. The Milky Way is not empty because we haven't found them. It is full because the mathematics demand it, full of possibility, full of unanswered questions, full of stories we haven't yet found ways to read. The atoms in your left hand are different from the atoms in your right hand. You breathe in oxygen and your body uses it, and it becomes part of you briefly before leaving on your next exhale. The atoms of your body are not permanent residents. They flow through you. Over the course of 7 years, most of the atoms in your body are replaced. You are not a fixed thing. You are a process, a temporary arrangement of atoms that were once inside stars, once inside the atmosphere, once inside other living things, now briefly organized into the pattern that is you. And when the pattern ends, the atoms continue into the soil, the air, the water, into other living things, into the future. The Milky Way does not waste anything. The universe is mostly darkness. Most of space is cold, empty vacuum. Most matter is dark and invisible. Most stars have already died or haven't been born yet. The brief, bright era of stars, the stelliferous era, astronomers call it, is a relatively short phase in the life of the universe. We happen to be living in it. We happen to be alive during the universe's luminous middle age, before it got too hot, after it cooled enough for matter to exist, right in the sweet spot, the window of time when stars burn, planets form, and life is possible. We are not just lucky, we are cosmically privileged. The Milky Way has arms with names. The main spiral arms are called Perseus, Scutum Centaurus, Norma, and Sagittarius. We live in a smaller feature called the Orion Arm, also known as the Orion Spur, a partial arm, a smaller structure connecting two of the major arms. It stretches roughly 10,000 light years in length and about 3,500 light years wide. Our entire neighborhood, named after the constellation Orion the Hunter, because that is the direction in which it extends when viewed from Earth. We named our corner of the galaxy after a pattern of stars that ancient humans drew a hunter in. The poetry of astronomy runs deep. The Milky Way has changed since it began. The early galaxy was a different place, denser, more active, with more star formation, more supernovae, more violence. The young galaxy was turbulent, loud, chaotic. As it aged, it settled. Star formation slowed. The galaxy calmed. Like a city that was once wild and fast and full of construction, and now moves at a quieter pace, older buildings, established neighborhoods, less noise. The Milky Way today is mature, still dynamic, still alive, but not what it was 10 billion years ago. Everything ages, even galaxy. There is a region at the center of the Milky Way called the Central Molecular Zone, a dense, turbulent region of gas and dust surrounding Sagittarius A*, containing enough material to form 60 million stars. Within it, star formation happens at extraordinary rates, intense, violent, chaotic. The center of the galaxy is still wild, still making things, still screaming with energy. While out here, in our quiet suburban Orion Arm, things are calm. The city center rages. The suburbs sleep. The Milky Way has a second center. Not a physical second center, but the second point of gravitational balance. In binary and multiple star systems, stable orbits can exist at points called Lagrange points, where the gravitational pull of two bodies balances out The galaxy, too, has structural features, regions of gravitational balance, resonance, patterns that give it the richness of structure beyond the simple pinwheel. Gravity is an architect, the most patient, most fundamental architect. It has been building the Milky Way for 13.6 billion years, and it is not finished. In the night sky of any planet in the Milky Way, the galaxy would be visible. From a planet in one of the spiral arms, looking inward, you would see a brilliant band of light denser and brighter than ours if the planet is closer to the center. From a planet far out in the galactic halo, the entire disk of the Milky Way would be spread below, a full spiral, visible in all its structure. There are places in this galaxy where, on a clear night, you could look out and see the whole spiral laid out against the dark. Home, seen whole. And somewhere in that view, one small, unremarkable star with one small, unremarkable planet, us. Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself." I have read that line 100 times, and every time I read it, I feel something shift. Not a sad feeling, not a small feeling, something large, something that stretches the universe, this 13.8 billion year old, 9.3 billion light year wide universe, arranged atoms into creatures that can ask questions about it, that can look up at the galaxy and wonder, that can feel wonder, that can feel anything at all. We are not separate from the Milky Way. We are part of it. We are the part that can look inward and ask, what is this? What am I? Where did I come from? And after 13.8 billion years of silence, the universe began through us to understand itself. The Milky Way will be here long after we are gone, long after every human being who has ever lived is dust, long after every building we have constructed has crumbled, long after every book is decomposed, every hard drive is corroded, every satellite has fallen from orbit. The Milky Way will still be here, spinning slowly. In the dark, it was here before the first cell divided in the first warm ocean. It was here before the first tree, before the first thought, before the first eye looked up at the sky and wondered. It will be here after all of that is gone. And when it is finally quiet after Andromeda's embrace, after the last star goes dark, after even the black holes evaporate, it will have been beautiful, all of it. This wild, spinning, 100,000 light-year wide home of ours, it will have been beautiful. And yet before all of that quietness arrives, there's so much still to say, so much still to see, so much still to learn about this galaxy we call home. Let us continue slowly. There's no hurry tonight. The galactic ecosystem, the Milky Way, is not just a collection of stars. It is an ecosystem, the most complex ecosystem we know of, a self-regulating, interconnected system in which the birth and death of stars, the flow of gas and dust, the gravitational interactions of billions of objects, and the chemistry of space all work together in a balance that has been maintained for over 13 billion years. In this ecosystem, nothing is wasted. When a star forms, it draws gas from the surrounding nebula, compressing it, heating it, igniting fusion. The newborn star then pours light and heat and radiation outward, which heats the surrounding gas, which changes the pressure balance, which influences whether nearby gas clouds collapse into more stars or disperse. Stars regulate the formation of other stars. When a massive star reaches the end of its life and releases its outer layers in a supernova, The shock wave travels outward through the surrounding gas. That shock wave compresses gas clouds, triggers new star formation, passes the baton. Death feeds birth. Birth feeds death, a cycle that has been running since the first stars ignited in the early universe, and that will continue until the last gas cloud disperses and no new stars can form. The Milky Way breathes, not in the way a lung breathes, not in seconds or minutes, in millions of years. Gas falls inward from the galaxy's halo, drawn by gravity toward the disk. It joins the reservoir of star-forming material. Stars form from it. The stars live out their lives. Some of them return their material to the interstellar medium when they die. Some of that material falls into the galactic disk again. The interstellar medium between the stars, space is not empty. We tend to picture the spaces between stars as pure vacuum and absolute nothing between the points of light, but it is not nothing. It is the interstellar medium, a diffuse mixture of gas and dust that fills the spaces between the stars, constituting roughly 10 to 15% of the total mass of the visible Milky Way. The interstellar medium is not uniform. It exists in several distinct phases, each with its own temperature, density, and character. The coldest phase, molecular clouds, are regions where hydrogen has combined into molecules. Dark, dense, opaque, temperatures of minus 260 degrees Celsius, just barely above absolute zero. So cold that atoms slow, almost to stillness. These are the places where stars are born. Within the molecular clouds, smaller regions called prestellar cores slowly collapse under gravity. The collapse takes millions of years. As the core compresses, it heats. As it heats, it begins to glow, infrared radiation. Invisible to the naked eye, detectable by the right instruments. Protostar, a star, learning to be a star. The warm phase of the interstellar medium, the warm neutral medium, fills the space between the cold clouds. Hydrogen atoms, not molecules. Temperatures around 8,000 Kelvin, vast in extent. And the hot phase, the hot ionized medium, is the most extreme. Plasma at temperatures of millions of degrees, generated by the shock waves of supernova explosions, less dense than anything humans have ever created in a vacuum chamber, but present throughout the galaxy at low concentrations. The galaxy is full of gas. In every phase, at every temperature, a complex, layered atmosphere between the stars. The dust, and in the interstellar medium, there is dust, cosmic dust. Not the dust on a bookshelf, not skin cells and fabric fibers. Cosmic dust is made of tiny solid particles, minerals, silicates, carbon compounds, formed in the outer layers of dying stars and scattered into space when those stars shed their material. These particles are small, typically a fraction of a micrometer in size, smaller than a bacterium. But there are so many of them that in dense regions of the galaxy, they are opaque to visible light. The dark lanes in the Milky Way, the dark patches in that band of light we see on a clear night, are not absence. They are dust clouds, blocking the light of the stars behind them. Dust is, in a sense, the memory of dead stars. Each dust grain was once inside a star, was cooked in the nuclear furnace of stellar interiors, were formed in the cooling outer layers as a star shed its mass, was scattered into space, has been drifting through the interstellar medium for billions of years. And when a new star forms, when a molecular cloud collapses, the dust falls inward with the gas. It collects in the protostellar disk around the young star. Grains collide and stick together. Larger and larger particles form. Eventually, rocks, eventually planetesimals, eventually planets. The dust of dead stars becomes the substance of new worlds. The rocky planets, Earth, Mars, Venus, Mercury, are made largely of material that was once inside stars that died before our sun was born. We live on the dust of ancient stars. We are made of the dust of ancient stars. Some of the most beautiful objects in the galaxy are the nebulae clouds of gas and dust illuminated by the stars within them or nearby. The Crab Nebula, the expanding shell of a star that was seen to burst by Chinese astronomers in 1054 AD. At its center, a pulsar, the neutron star left behind spinning 30 times per second, powering the glow of the surrounding cloud with its magnetic field. A star that ended its life almost 1,000 years ago, its expanding remains still visible, still glowing, still moving outward at 1,500 kilometers per second. The pillars of creation, vast columns of gas and dust in the Eagle Nebula, shaped by the winds and radiation of nearby young stars, up to 5 light-years tall. Inside each pillar, the pressurized gas is collapsing, new stars forming within the columns, even as they are being eroded from the outside. Creation and erosion happening simultaneously. The Cat's Eye Nebula, the dying breath of a star like our sun, its outer layers expelled in a complex, symmetrical shell around the white dwarf at its center. The intricate, layered structure, rings within rings, knots and jets and concentric shells, formed over thousands of years as the star shed its mass in multiple episodes. We do not fully understand how the Cat's Eye got its structure. The physics of stellar mass loss is still an area of active research. The galaxy is full of things we cannot fully explain. The Helix Nebula, sometimes called the Eye of God, a shell of gas expelled by a dying star, stretching 2.5 light-years across, with a warm white dwarf at its center and a cooler outer ring that glows in infrared. When Hubble photographed it in detail, the result was an image so striking, so unexpectedly reminiscent of an enormous eye in space that it became one of the most widely shared astronomical photographs ever taken. The galaxy did not intend to make an eye. It does not intend anything. It simply follows its physics. And sometimes the physics makes something that looks to creatures who see with eyes like it is looking back. Globular clusters. On the outskirts of the Milky Way, in the spherical halo that surrounds the disk, there are ancient structures called globular clusters, spherical, dense collections of stars. Hundreds of thousands, sometimes millions of stars packed into a region only a few hundred light-years across. The stars in globular clusters are old. Among the oldest in the galaxy, some clusters contain stars that are 12 to 13 billion years old, formed in the earliest phases of galactic history before the disk of the Milky Way had fully taken shape. These stars have been burning for almost as long as the universe has existed. They have outlasted the galaxies they were born in. They have survived the mergers and interactions that shaped the Milky Way. They have watched from their high-altitude orbits above the disk as the galaxy built itself below them. Ancient witnesses, still burning, if there are planets around the stars of old globular clusters, and some evidence suggests that maybe those planets have been orbiting for 12 billion years. 12 billion years. For context, the Earth has existed for 4.5 billion years. Life has existed on Earth for about 4 billion years. Complex animal life has existed for roughly 600 million years. Human beings have existed for about 300,000 years. A planet that formed in a globular cluster 12 billion years ago would have existed for nearly 3 times the age of the Earth. Whatever might have arisen on such a planet, what forms life might have taken, what complexity might have emerged over that unimaginable span is entirely beyond our current ability to envision. We can barely imagine 4 billion years. 12 is a different order of time entirely. The galactic halo, beyond the visible disk of the Milky Way, beyond the spiral arms, beyond the central bar, beyond even the outermost regions of detectable starlight, there is another structure, the galactic halo, a vast, roughly spherical region surrounding the disk, extending perhaps several 100,000 light years in every direction. The halo is not empty. It contains the oldest stars in the galaxy, the high-velocity stars of the thick disk, the stars of the globular clusters, individual stars scattered in low concentrations through the volume. It contains the stellar streams, the ghostly arcs of stars stripped from ancient dwarf galaxies, still tracing the orbits of their destroyed parent systems. And it contains the dark matter halo, the invisible, enormous structure of dark matter that encompasses everything, that provides the gravitational framework within which the visible galaxy exists. The dark matter halo is larger than the visible galaxy, much larger. The visible disk of the Milky Way, the part we can see, the spiral structure we photograph and study, is embedded within a dark matter halo that may extend 1 million light years or more in every direction. We live at the center of something vastly larger than what we can see. As is so often the case, stellar population, astronomers divide the stars of the Milky Way into populations, categories that reflect their age and composition. Population I stars are young, metal-rich stars, the ones that formed from gas that had already been enriched by earlier generations of stellar evolution. Our Sun is a population I star. These stars are found primarily in the spiral arms of the disk, where star formation is active. The word metal in astronomy has a specific meaning. To an astronomer, any element heavier than hydrogen and helium is a metal. Oxygen, carbon, iron, silicon, all metals in the astronomical sense. Population stars like our Sun are relatively rich in these heavy elements because the gas from which they formed had been processed through many generations of earlier stars. Population II stars are older, metal-poor stars formed from gas that had not yet been significantly enriched by stellar evolution. They are found in the galactic halo, in globular clusters, in the bulge. Their spectra show far less iron, far less calcium, far less of the heavy elements that enrich the material of younger stars, and theoretically not yet observed directly, but inferred there should be population III stars. The first stars, formed from pure hydrogen and helium, with no heavy elements at all. No carbon, no oxygen, no iron. These stars formed in the first few 100 million years of the universe's history before any heavy elements existed. They were probably massive models, suggested without heavy elements to cool the gas, the collapsing clouds formed very large stars. And they lived fast and ended quickly, releasing the first heavy elements into the universe when they completed their lives. The first carbon in the universe, the first oxygen, the first iron, all forged in the fiery, brief lives of population III stars that no longer exist. We have not directly observed the population III star. They are gone, but their legacy is in every heavy element in the universe. In every oxygen atom in your lungs, in the iron in your blood, the first stars gave themselves entirely to the universe, so that everything else could exist. Variable, stars and pulsars. The night sky appears fixed and permanent. An illusion. Many of the stars we see change their brightness, varying over hours or days or years, in patterns that carry information. We have already spoken of Cepheid variables, the pulsating stars that serve as distance markers, their periods of brightening and dimming tied precisely to their intrinsic luminosity. But there are other kinds of variable stars. Long-period variables, red giant stars that pulsate over periods of months to years, swelling and contracting in cycles driven by complex processes in their interiors. Mira, the most famous, brightens and dims over a period of about 332 days, changing in brightness by a factor of several thousand. To the naked eye, it appears and disappears. Ancient observers who noticed it called it Mira the Wonderful. It is still doing exactly what it has always done, brightening, dimming, over and over, for billions of years. RR Lyrae variables, older, smaller pulsating stars found in globular clusters varying over periods of less than a day. They too serve as distance indicators, their pulsation period tied to their luminosity. And then there are the stranger variables. Be Cephei, stars, massive, hot stars that pulsate due to pressure waves in their interiors, their brightness changing in patterns with periods of hours. Symbiotic stars, binary systems in which a giant star and a white dwarf orbit each other, material flowing from one to the other, producing irregular eruptions of brightness. Cataclysmic variables, another class of binary systems, in which material from a companion star falls onto a white dwarf and periodically ignites in a thermonuclear flash, producing what is called a nova, not a supernova. A nova, the white dwarf survives. The explosion blows off the accreted material, and then the cycle begins again, material accumulating, building up until the next ignition. Some novae recur on timescales of decades, some on timescales of centuries. The night sky, if you watch it long enough and carefully enough, is in constant motion, brightening and dimming and erupting and pulsing, a living thing. Binary stars, most stars in the Milky Way are not alone. It is easy to imagine stars as solitary objects, isolated points of light, separated from their neighbors by light years of empty space. But the majority of sun-like stars and a significant fraction of all stars exist in pairs or groups, binary star systems. Two stars orbiting their common center of mass, locked together by gravity, their fates entwined. Some binary pairs are wide separated by hundreds or thousands of astronomical units, orbiting each other so slowly that their period is millions of years. From a planet in such a system, the companion star would appear as nothing more than an unusually bright star in the sky, moving imperceptibly from year to year. Some binary pairs are close, separated by only a few stellar radii, orbiting each other in days or even hours. In these tight pairs, the stars raise enormous tidal forces on each other. They distort each other's shapes. Sometimes they transfer mass from one to the other. And when one of the stars in a close binary is a white dwarf, the dense, compact remnant of a medium-sized star, and the other is a normal star still in its main sequence, the stage is set for something remarkable. Material flows from the normal star to the white dwarf. It accumulates on the surface. The pressure builds, and then ignition, a nova, hydrogen fusing in an explosive layer on the surface of the white dwarf, briefly making the system millions of times brighter. And if the white dwarf accumulates enough mass, crosses a threshold called the Chandrasekhar limit, the entire white dwarf undergoes a thermonuclear reaction. Not just a nova, a type E, a supernova. The entire star consumed in seconds. A flash of light bright enough to be seen across the universe. These type Ia supernovae are remarkable tools for cosmologists. Their peak brightness is so consistent that they serve as standard candles, allowing astronomers to measure distances across billions of light years. It was through Type Ia supernovae that astronomers first discovered in 1998 that the expansion of the universe was accelerating, that dark energy was real, that the universe was not just expanding but speeding up. A discovery that changed our understanding of the cosmos, made possible by the explosion of a white dwarf in a binary system, made possible by a star that ceased to exist in an instant after billions of years of quiet accumulation. Even in ending, stars teach us things. The galactic center. Let us go for a moment to the center of the galaxy. Not the black hole itself, we will leave some mystery intact, but the region around it, the central molecular zone, a dense, turbulent region of gas and dust within the inner few hundred light years of the galaxy, containing enough raw material to form tens of millions of stars, churning with activity. The star formation rate near the galactic center is far higher than in the disk. New stars form rapidly in the dense gas, live fast, and end in supernovae that further compress the surrounding material and drive more star formation. There are massive young star clusters near the galactic center, the Arches cluster, the quintuplet cluster containing some of the most luminous stars known in the Milky Way, stars burning 1,000,000 times brighter than the sun, stars so massive and so hot that they shed their outer layers as fast as they fuse their interiors. These stars will live for only a few million years. In the disk, a star like the Sun lives for 10 billion years. Near the galactic center, the most massive stars live and end in the blink of an eye. The galactic center is not calm. It is the most energetically active region of the galaxy, a continuous cycle of star formation, stellar life, supernova, shockwave, new star formation, louder, brighter, more dynamic than anything in our quiet corner of the Orion Arm. From the galactic center, the rest of the galaxy would appear as a vast disk of stars, a horizon of light in every direction, the density of stars so high that the night sky would glow far brighter than it does from Earth. There would be no darkness. Not really. In every direction, stars, more stars than we see in our entire night sky, visible from any single point on Earth. The sky made of starlight, magnetars. In the category of strange things the Milky Way contains, few are stranger than magnetars. A magnetar is a type of neutron star, the extremely dense remnant of a massive star's core, left behind after supernova, but not an ordinary neutron star. A magnetar has a magnetic field so strong that it exceeds anything else in the known universe. The magnetic field of a magnetar is approximately 1 quadrillion times stronger than the Earth's magnetic field. 1 quadrillion. At such field strengths, strange things happen. The quantum vacuum, the empty space around the star, becomes birefringent, splitting light into different polarizations. Atoms are distorted, stretched into long, thin cylinders along the field lines. The chemistry of matter, as we know it, no longer applies. And the magnetar is not passive. Periodically, the immense stress on the star's crust, driven by the shifting magnetic field, causes what is called a starquake. The crust cracks, the magnetic field reconfigures, and in an instant, a burst of gamma radiation and X-rays is released, a magnetar flare. The most powerful magnetar flare ever detected released more energy in 1/10 of a second than our sun emits in 100,000 years. In 1/10 of a second. The flare was detected by satellites and ground-based observatories alike. It briefly saturated detectors designed to observe objects far less energetic. The source, SGR 1806 to 20, a magnetar about 50,000 light years from Earth. 50,000 light years away, and still powerful enough from that distance to affect instruments on Earth. Fast radio bursts. In 2007, astronomers reviewing archival data from a radio telescope found something they could not explain. A brief, intense burst of radio waves, lasting only a few milliseconds, coming from far outside the Milky Way, and containing in those few milliseconds as much energy as the sun emits in 3 days. They called it a fast radio burst. Since then, hundreds of fast radio bursts have been detected, some repeating, some appearing only once. Their origin was, for years, almost entirely mysterious. The best current explanation: magnetars. When a magnetar produces a starquake and releases its burst of energy, some of that energy may escape as radio waves that travel across the universe, arriving at our radio telescopes as a brief, bright flash. We cannot see the magnetar that caused the fast radio burst. Too far away, too brief, we see only the echo, a shout from across the universe, lasting milliseconds, telling us that something extraordinary happened, billions of light years away, millions of billions of years ago. The universe communicates in flashes. We are only beginning to learn to read. Gravitational waves. For most of human history, we have experienced the universe through light, visible light, then radio waves, then X-rays, then infrared, then gamma rays. Each new wavelength of the electromagnetic spectrum revealed a different face of the universe. Objects invisible in visible light blazing in X-rays, objects invisible in X-rays glowing in radio. Each new way of seeing transformed astronomy. And then, in 2015, we opened a completely new sense: gravitational waves. On the 14th of September 2015, at 9 hours 50 minutes and 45 seconds UTC, the LIGO detector in Livingston, Louisiana, detected a minute distortion in space, a stretching and compressing of the distance between two mirrors, each suspended at the end of a 4-kilometer arm. The distortion was tiny, about 1,000th the diameter of a proton. It lasted less than a second. And it was caused by two black holes, each about 30 times the mass of the sun, spiraling together and merging over 1 billion light years away. The merger released energy equivalent to 3 solar masses, 3 entire suns worth of energy in less than a second, in the form of gravitational waves, ripples in the fabric of space-time itself. And those ripples, spreading outward at the speed of light, arrived at Earth 1 billion years later and moved our mirrors by 1,000th the diameter of a proton. And we detected it. This detection, announced in February 2016, confirmed the prediction Einstein had made in 1916, 100 years earlier. It opened gravitational wave astronomy. Since then, dozens of gravitational wave events have been detected: black hole mergers, neutron star mergers, and combinations thereof. Each one a messenger from the invisible universe. Each one telling us something about objects we cannot see. The universe is speaking in a language we have only just learned to hear. Dark matter deeper. We have spoken of dark matter already, but let us go deeper. The evidence for dark matter is not based on a single observation. It comes from many independent lines of evidence, all pointing to the same conclusion. The rotation curves of galaxies, the observation that stars in the outer parts of galaxies orbit too fast for the visible matter to explain. The gravitational lensing of galaxy clusters, the way light is bent by the gravity of clusters, by more than the visible matter can account for. The cosmic microwave background, the pattern of temperature fluctuations in the earliest light of the universe, whose structure can only be explained if dark matter was present in the early universe, influencing the growth of the first structures. The large-scale structure of the universe, the web of filaments and voids that can only be reproduced in computer models if dark matter is included. All of these independently point to the same thing. There's more matter than we can see, about 5 times more. And we do not know what it is. This is not a comfortable position for science to be in. The most abundant form of matter in the universe, the substance that provides the gravitational scaffolding for everything that exists, is unknown to us. We cannot touch it, cannot detect it directly, cannot identify it. We know it is there only by what it does to everything around it. Like knowing there is a strong wind, not by seeing the air, but by watching the trees. The dark matter is the wind. We are still looking for the air. The future of astronomy. We are at the extraordinary moment in the history of astronomy. The James Webb Space Telescope is observing the first galaxies that formed in the universe, their light reaching us from 13.1 billion years in the past. The Event Horizon Telescope, a planet-wide network of synchronized radio telescopes, has produced the first image of a black hole, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. And in 2022, it produced an image of Sagittarius A times the black hole at the center of our own galaxy, the thing at the center of the Milky Way, the 4 million solar mass point around which we all orbit, photographed a ring of glowing gas around the dark center, the eye of the galaxy, looking back at us. Future telescopes, arrays of instruments in space, distributed across orbits, baselines spanning millions of kilometers, will resolve objects in more detail than we can currently imagine. The Laser Interferometer Space Antenna, if launched, will detect gravitational waves from supermassive black hole mergers across the observable universe. The Square Kilometer Array will map the hydrogen gas of the Milky Way and nearby galaxies with unprecedented resolution, revealing the full structure of the interstellar medium. The Roman Space Telescope will conduct wide-field surveys of the galaxy, finding hundreds of thousands of exoplanets through gravitational microlensing. We are at the beginning of seeing clearly. The century ahead may reveal more about the Milky Way than all previous centuries combined. The galaxy is patient. It has been waiting to be understood for 13.6 billion years. A few more centuries will not trouble it. The pale blue dot. In 1990, as the Voyager 1 spacecraft was about to pass beyond the outer planets, astronomer Carl Sagan made a request. Turn the camera around, point it back toward the inner solar system. Take a photograph of Earth from 6 billion kilometers away. The image that came back showed a tiny, bright speck, less than a pixel, suspended in a ray of sunlight. A pale blue dot. Sagan wrote about this image with a clarity and depth that has not been surpassed in the 3 decades since. He noted that on that dot, that mote of dust suspended in the sunbeam, every human being who had ever lived had lived their entire life. Every king, every slave, every saint, every murderer, every moment of joy and suffering and love and loss in the entire recorded history of our species. All of it on the pale blue dot in one small corner of one small spiral arm of one average galaxy in a universe containing 2 trillion galaxies. The image does not make human experience small. It makes it precious. The universe is vast and old, and mostly dark and cold and empty, and somewhere in it, on one small rocky world, around one ordinary star, matter organized itself into something that could look at the universe and feel moved by it, that could hear a description of the galaxy and feel wonder, that could lie down at the end of a day and look at the night sky and know, in some partial and imperfect way, what it is looking at. We are the universe's way of being amazed by itself. That is not nothing. That is perhaps everything. The long night. It is late now. The world outside, wherever you are, is quiet. The traffic is stilled. The voices have faded. The particular familiar sounds of your particular familiar life have retreated to wherever sounds go when the world is sleeping. And somewhere above you, above the ceiling, above the roof, above the clouds and the atmosphere and the thin shell of air that makes this world habitable, the Milky Way continues, slowly turning. That slow, patient, ancient turn. One revolution every 225 million years. Since you began reading these words, since the first sentence about 4 million suns, the galaxy has turned by an amount so small it cannot be measured by any instrument we possess. It will be turning when no instrument exists to measure it. Still turning when the last light of the last star has faded and the universe enters its long, cold, dark final age. The galaxy is not in a hurry. It has never been in a hurry. 13 billion years, and still it moves at the same ancient pace. There is something in that pace, something in the sheer, indifferent patience of a galaxy that feels, on a quiet night, like permission to slow down, permission to stop for a moment, the relentless forward motion that the days demand, permission to be still. The atoms in your body right now, the carbon, the oxygen, the nitrogen, the hydrogen, were not always in your body. They will not always be in your body. They are passing through, briefly organized into the particular pattern that is you, the particular arrangement of atoms that thinks these thoughts, that feels this tiredness, that is beginning slowly to let go of the day. Before they were in you, those atoms were in the air, in the food you ate, in the water you drank, in the bodies of other living things that lived and died before you were born. And before that, they were in the ocean, in the atmosphere, in the rocks. And before that, much further back, they were in a star that completed its life before a sun was born, that scattered its material into the galaxy, that became part of the cloud of gas and dust from which our solar system formed. You are not separate from that history. You are the current chapter of it. The atoms that are, for this brief moment, you will continue after you, into the soil, the air, other living things, the ocean. Over millions of years, they will cycle through the earth. Over billions of years, they may be incorporated in the next generation of stars. You are part of the galaxy's cycle, not metaphorically, physically, chemically, in the most literal sense. The quiet of deep space. Think of the space between the stars, not the space between planets, the few light hours of our solar system, which by astronomical standards is almost cozy. The space between stars. The nearest star to our sun, Proxima Centauri, is 4.2 light years away. In kilometers, approximately 40 trillion. If you shrank the sun to the size of a grapefruit and placed it on a table, Proxima Centauri would be another grapefruit approximately 1,700 kilometers away. Between them, almost nothing. Some gas, some dust, some cosmic rays, vast, cold, dark, nothing. This is most of the galaxy. Most of the Milky Way, most of those 100 billion stars, is the emptiness between them. We tend to think of the galaxy as a dense, brilliant structure. When we picture it, we see the glowing disk, the bright center, the sweeping arms, But if you were in interstellar space, you would not see this. You would see stars, bright points, scattered across the dark sky, fewer than you might expect and farther apart than feels intuitive. You would see the band of the Milky Way, the accumulated light of the disk as we see it from Earth, and you would feel, if you let yourself feel it, the weight of the emptiness, the vast, cold, patient emptiness between the stars, which is not nothing, which is the interstellar medium and dark matter and cosmic rays and the faint background radiation of the Big Bang, but which is, by every measure, extraordinarily close to nothing, and which is somehow peaceful. The small things in the scale of the Milky Way, the Earth is almost beneath mention. Our sun, one star among hundreds of billions, is itself almost beneath mention. And on one rocky planet circling that ordinary star in a quiet suburb of an average spiral galaxy, there's small, warm, soft creatures who have developed the remarkable ability to be curious about the universe, to ask questions, to look up and slowly, imperfectly, with instruments and mathematics and decades of patient observation, to begin to understand what they're looking at. This is the most improbable thing the Milky Way contains. Not the black holes, not the magnetas, not the neutron stars spinning 716 times per second. The curiosity, the wonder, the small animal lying on its back in a field, looking at the stars and feeling something shift inside it, feeling small and vast at the same time, feeling alone and connected at the same time, feeling the weight of the cosmos and finding it somehow comforting. This is the strangest and most extraordinary thing in the galaxy. The final facts, one last set of things to carry with you into sleep. The universe is 13.8 billion years old. If that entire history were compressed into a single calendar year, a cosmic year, beginning with the Big Bang on January 1st, the Milky Way would form in mid-January. The sun would ignite in early September, the Earth would form in mid-September, the first life on Earth would appear in late September. The first animals with hard shells, the Cambrian explosion, the first complex animal life would appear on December 17th. The dinosaurs would appear on December 25th. They would end on December 30th. Homo sapiens, our species, the entire history of human beings would appear in the last 10 minutes of December 31st. All of recorded human history, from the first cities, the first writing, the first empires, would fit into the last 20 seconds of the last minute of the last hour of the year. Everything you have ever read, every war, every discovery, every name you know, every story ever told, 20 seconds. The Milky Way has been here for most of the year. We have been here for 10 minutes. And in those 10 minutes, we have looked up, we have asked questions. We have begun to understand. That is not nothing. In 10 minutes, we figured out what year it is. The galaxy will be here tomorrow. It will be here long after tomorrow. Long after everything you are worried about tonight has resolved itself, one way or another. Long after every concern that is keeping you at the edge of sleep has dissolved into whatever concerns become when we stop holding them. The Milky Way turns patiently at the same speed it has always turned. One revolution every 225 million years. And you can rest. Not because your concerns are small, they are not small to you, and that is exactly as it should be. But because the universe is large enough to hold them, because there is something outside the window tonight, above the streetlights, above the clouds, in the dark between the stars, that has been here for 13 billion years and will be here for billions more. And in the face of that patience, that scale, that ancient and indifferent and somehow comforting immensity, The day can end. The thoughts can slow. The weight can lift just a little. Let your breathing find its own pace. In and out, in and out, slow, slower. Somewhere above you, the light of a star that is 1,344 light years away is arriving at your atmosphere right now. It left that star when the year was approximately 680 AD. It has been traveling ever since. And tonight it arrives at Earth, at your sky, at this night, patient, as all light is patient, as the galaxy is patient, as the universe enormous, ancient, full of things we have not yet learned to see is patient. It can wait. You are allowed to sleep. The atoms in your body were forged in stars. They know the way home. They have been resting and waking and cycling through the galaxy for billions of years. They know how to rest now. So do you. Close your eyes. The Milky Way turns. The stars burn their patient fires. The dark matter holds everything together in its invisible embrace. The cosmic web stretches in every direction, vast and strange and full of things we have not yet named. And here, on a pale blue dot, in one quiet corner of one ordinary galaxy, you are here, for this moment, for this night, alive in the brief, bright, luminous era of stars. Part of the galaxy's long story, part of the universe's patient unfolding. Sleep now. The cosmos continues. It will be here in the morning. It will have been beautiful. Still, always, closing the long fade. So here we are, 100 things about the Milky Way. The galaxy is ancient. It is enormous. It is mostly invisible, mostly silent, mostly empty, and yet it contains everything. Your atoms came from it. Your planet formed inside it. Your breath, in this moment, is made of material processed in the hearts of dead stars. You are not small because the galaxy is large. You are large because the galaxy is in you. Let that settle. Now, let the mind go quiet. Let the thoughts slow down the way stars slow as they drift to the outer edges. You are inside something ancient and enormous and alive with its own kind of motion. And for now, right now, in this moment, you are here, in the Orion Arm, on a small rocky planet, warm, breathing, alive, in the Milky Way, our galaxy, our home. Close your eyes. Drift. The stars will be there when you wake up. They always are.